All right. So first off, we are going to talk about your next assignment, guys. This is going to be assignment number 7. This is it. And let me check again. Just a second. I want to be sure. Certain. Okay. So guys, assignment number 7. This is going to be, again, you have to do something empirical, namely actual literature review. So one of the things that you need to mention here is this. When a variable interests are considered, you find a lot of times you're going to see autoregressive models involved. Okay, so that's basically what you have. Okay, and I want you to basically there are certain applications which are listed. Okay, namely among others, wages, unemployment, and productivity, a common relationship, whatever, which is examining foreign direct investment, stock market development, and economic growth, energy consumption versus pollution, trade and exchange rates, blah, 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 so financial development, inequality, and the list goes on. So you have also stock prices, commodity prices, and cryptocurrencies. Again, this is actually examined, okay, and it's done mostly by using some sort of autoregressive models. Now, I don't want you to analyze this from the formal perspective. I would just like you to write some sort of literature review, or basically a brief meta-analysis of the topic of the choice, which considers autoregressive models from the empirical perspective. Okay, so some sort of result might be basically indicated through these models. And I would like you to basically to consider a topic, and that you would need to write some sort of a review. Okay, so maybe a literature review, maybe reviewing the results, whatever, of the topic of your choice. And please select a field from finance or or economics. Actually, it's economics most of the time. And yeah, so you should basically pay attention to the principles, okay, of scientific research. That's, again, so that was from last week, which we have already considered. Okay, so lectures 11 and 12 are involved. And I want you to basically to select a topic on your own. Basically, you're interested in it would be good. And I want you to present it in a scientific approach. Now, please write an abstract. So I have forgotten this to write it down, but please write an abstract. So basically what your key results are, summarizing maybe 2 or 3 key results that you find in the literature. This is basically, again, that are linked to your topic, of course. And then please also write an introduction, okay? Even though you might basically come straight to the point. Okay, so maybe the introduction is optional if you find that basically from the structure doesn't fit your purpose. But since it's basically, you can consider that to be a short meta-analysis, you can basically write an introduction. So I would recommend you to do so. But I'll let you convince basically me doing otherwise. Now, do not exceed 2 to 3 pages max. Okay, so that should be your. It depends on the format, and I understand that. So font size, this and that, whatever, but it definitely should not be more than 3 pages. And yeah, so a short review, okay, whatever you come up with, let's say within a week. Okay, so you have actually 7 days left, or 8 days basically, and that should be fine. Yeah.
Those 3 pages, they should include abstract, introduction, the analysis and results.
Yes, but again, so only from the empirical perspective. So you don't need to analyze that from the formal perspective, okay? So you don't need to basically consider equations, whatever, okay? Even, or maybe if you find this important in terms of, illustrating what these things are, or maybe they adjust, the models that they estimate somehow, of some sort. Yes, that's fine. So I'm not basically predominant in this part. I'm not interested in you basically dealing with equations that you mostly not likely not to be able to understand. Maybe if you want to illustrate a regression model or compare multiple regression models, then it could be a good idea to basically consider regression equations. I'm not sure, okay, but I'll let you convince me in this subject or in this matter, okay? but you would not need to. So you can simply say AR models, ARMA models, ARMA models, maybe. I'm fine with that. So you don't need to elaborate on the models themselves, rather than you're focusing on the results. And I want you to summarize the results, the empirical results that you find to your subject. And that's it. Okay? So again, you can basically, I give you a list here of possible topics that you might consider. Okay, so here there are. And yeah, so this is basically what you could do. I'm not saying what you should do, I'm saying what you could do. Okay, but again, so that's basically what you, what you're supposed to do anyway. So when you basically do an empirical analysis on your own, but you don't need to. So that would be too short, okay, for 2 to 3 pages if you include an empirical analysis. But let's say in a second step, you would also incorporate an own empirical analysis into your paper. Then you would need to adjust the introduction, and then you would need to adjust the paper itself. But you have at least some sort of draft, and you have an idea what the results are. Okay, so even before you would consider your own empirical research, and then, yeah, that's what you would do, actually. So you would become familiar with the topic. And I want you to become a little bit familiar with the topic, and basically pointing out some major results that are involved. And yeah, so that should be fine, actually, in that regard. Okay, so I would teach you, I would tell you how to and what to focus on and what to consider and what not. So again, I want to have a review, more or less, not a detailed description of theoretical models that I do in the lecture, more or less. So I try to, at least, so you don't need to tell me that ARMA models are used basically to capture relatively large AR processes and this and that. So that's not your goal, okay? Or it's not your goal basically to elaborate on stationarity. If you consider, let's say, ARMA models, then you might be telling me, so here and there, what is an ARMA model, okay? In that regard, so in the context of stationarity maybe, but you should keep it short. So just for the reader to understand what is behind all that stuff, but not predominantly focusing on equations. Again, maybe you want to basically, you should keep it short. So maybe you want to drop some equations when you try to compare different approaches, okay, regarding model estimation, for example. This is something that you can do, okay? But I'm not saying you have to. Maybe you could do it if it fits to your purpose. But if it doesn't, why would you, okay? But pay attention, if you drop some equations here and there, you should adjust the notation, okay? So since they're coming from basically different papers and different sources, they use different notations themselves, so you would need to adjust this, okay? Or maybe you provide a list, what they're estimating, which are the dependent variables, which are the, some sort of a table, explanatory variables, this and that, and, or whatever, if basically multiple variables are involved, and you should basically summarize the results. And yeah, I'll let you decide. So maybe you would be considering, providing some sort of a table just for an overview. Maybe it's easier to read, but maybe it's not. So again, I don't really insist on doing that. Okay, but I think if you provide an overview, it could be helpful, but I'm not saying it is. So again, I let you decide. Okay, if you go beyond 3 pages a little bit, then it should be fine, but you should definitely not submit 5 pages or so. That's too much, probably. Okay, you should focus on the main things that are involved. Okay, so that's not a thesis, guys. Okay, even if you would do that. So try to keep it short, and you might find that it's basically better if you increase the content density rather than the number of pages. Okay. So when I was a student, I was practicing this, and a lot of people asked me to do that. So they turned me, let's say, 30, 40 pages, and I made it to, basically in the first step, to be 15 to 16 or something, without cutting the content, you know, and not, you know, editing it. So just basically, you know, using different explanation style, because usually when it comes to journals, they have a maximum pages and a maximum number of pages that they don't want you to, I mean, if you submit there, they don't want you to exceed, okay? Depending on basically a perspective. I don't think you would need them. I'm not sure, but you would try what kind of diagrams or charts you would need to show me. But maybe some sort of development of the time series if that is important. But please do this on your own. But again, I want you to summarize basic results. So it's not about, you know, charts. You could make a reference to those if you have basically that displayed in different works. I think I would choose that. And you would basically, you know, maybe in a footnote or something like that. Again, so I want you to summarize results, okay? And I want you to basically I want you to make me become familiar with your topic then, okay? So it's basically more important how you structure it rather than the information that you provide, okay? Because again, it's not difficult to provide information about papers, all right? You need to, but these are just, you know, the tools that you have. You need to bound it together, let's say. And I want you to do that. So, yeah, please do that. All right? Okay? Okay, guys. Yeah, so the deadline is next week. And as usual. Okay? So that will be the 7th assignment. Okay? After that, you have an 8th, which is related to this subject that I'm talking to. I mean, I will basically explain to you right now. Okay, guys. Yeah, that's it. And yeah. So I hope this is understandable. So some sort of any literature review, maybe the topic, I mean, hopefully, maybe you choose a topic that you are also interested in. Okay, guys. Yeah, so that's going to be your next assignment. And then we are going to consider lecture 14. And lecture 14, we talk about, this is going to be a technical one. So I'm going to talk about asymptotics predominantly. And that's what it's going to be. So I will use different styles of convergence and whatever. This is more or less a, you know, a review of statistics, but also in the context of time series. The first thing that I want to consider is convergence and distribution. You heard this a lot of times, actually, so far, but I was not defining it, and I choose to incorporate this into the lecture because people are not certain regarding these things. So I would basically consider the following. So you have a sequence of random variables, guys. So that's a sequence, okay? And the format is changing. I don't know why this is. Okay, so the format of the slides. Okay, anyways, so the random variables, x1, x2, and so on, are the sequence, and that is a sequence, okay? And you have some sort of a convergence of a sequence, but not basically the regular convergence that you are familiar with, you might be familiar with. You have a sequence regarding convergence in distribution. So it's not the random variables that converge, actually. It's a distribution that it basically does that. And the distribution is expressed by the CDFs, okay? So cumulative distribution functions. Those are the things that are involved. So you have a convergence of functions, and it is done as follows. So they converge in distribution, okay? Or they set to be converging in distribution to another random variable, but actually it's not the random variable that they converge to, but this is how it's expressed. It's their distribution functions that they converge. Okay, so the random variable, which is the limit, has a distribution function f, so that will be the limiting distribution function. And they set to do this. This is denoted by the following notation. So xn is a sequence, okay? And that converges in distribution, so this is how it's denoted, to another random variable. Okay, so but keep that in mind, guys. This is not a regular convergence because these are random variables that converge. But again, this is just an abstract notation. It's not directly the random variables that do converge. Okay, so and as basically the sample size increases, so n is a sample size all the time. And let's say, I mean, in a practical perspective, n is a sample size, so you increase the sample size, and what does happen basically to the sequence that you define? Now, the sequence is supposed to converge to a limit in distribution if the cumulative distribution functions converge. And they do just simply that. So it's a limit going to be of the functions. You know what limits of functions are. I mean, you have a lot of examples that you saw during your studies. And the limiting distribution function is the distribution function of the limit random variable, basically, which is x. And that's it, actually. So it's not directly the random variables that do converge, however we refer them to as such, because we say that they converge in distribution. It's the cumulative distribution functions that do the job. And that's what I'm basically defining here. Okay, now there are some restrictions regarding continuity of the limiting CDF, so of the limiting, but that's something that you will not need to worry about here, at least in this part. And I'm not going to consider examples related to this, but again, so I will skip it. So that's the first part, okay, convergence in distribution, a very important concept. So one example, for example, I will consider the central limit theorem. I will have random variables that converge to the normal distribution, which means that their cumulative distribution functions would converge to that of the normal distribution, and usually it's standardized so that you would consider the standard normal distribution, but not all the time. Anyways, I will come back to it later on. The next concept that I'm considering is convergence in probability. Convergence in probability is a different concept. Keep in mind, guys, that although it is, literally speaking, convergence in probability, there is a probability that will converge, namely to 0, and I will let you know which probability that would be, okay? So this is a concept that is denoted by, P, okay? So anytime you see basically an error, okay, where you have a sequence of random variables converge to maybe to another, okay, so that's going to be the limit. Keep in mind that the limit can be also a constant. In this case, it's not true basically for convergence and distribution, but it is true basically for, let's say, convergence in probability, from the practical perspective. So it can be a constant. For example, the weak law of large numbers will exactly be that, but again, I will talk about that later on. If the following probability, okay, that's just a different notation. So this is the probability limit, guys. So P lim, okay, that's the probability limit. So the probability limit of these random variables is going to be, might be another random variable, maybe a constant sometimes, okay. So again, a weak law of large numbers we refer to as a constant, but I will consider that if the following probability will converge to 0. So this means the following. So the limit of the following probability, and I will define the event. The probability that the sequence, okay, exceed, or the distance of the members of the sequence to the limit exceeds a certain value. Okay, so if you take, for example, the absolute value of a member to the limit, this is the distance, okay, so what you see here, distance of the sequence to the limit, okay? And this means that the distance between the sequence, between the members of the sequence to the limit will exceed a certain value. So it's going to be greater than epsilon, whatever, basically how you would specify it. Now the probability that the distance of the members to the limit will exceed a certain value is converged to 0 for every single distance there is. Okay, so for every single distance there is, okay, the probability that members exceed that distance to the limit will converge to 0. This is convergence in probability. You understand that? This is a relatively weak concept of convergence. Okay? That doesn't mean that basically the observations do. That means that the probability does. So the probability is converging to 0 as the sequence progresses. Namely, probability of what? The probability that members exceed this, the distance of members exceed basically, the distance of members to the limit exceed a certain value. And that's what it's basically, what it will be. So however small the distance might be, okay? So the probability will converge to 0 of the event that members have distances to the limit that exceed a certain value. Is it clear, guys, more or less? Okay, so again, keep in mind, when it comes to convergence and probability, it is a probability that converges, namely to 0. So you can say maybe that the probability that the sequence does not converge to the limit is going to be converging to 0, right? Because you have some sort of divergence here in this case, okay? So actually this is what convergence and probability is. A relatively weak concept, by the way, but that's not important. So you would say unusual events. What are unusual events? Unusual events are, for example, that, again, I mean, this is what it means, okay? Literally speaking. So members or distances of limits of members to the limit would exceed a certain value. That's unusual in that regard, okay? And the probability, let's say, of unusual events converges to 0 as basically the sequence progresses, or in practice you would say as the sample size is increased. That's it, okay? So this is basically how you would progress, okay? And that refers to the weak law of large numbers also, which I'm going to introduce, but I will look at this concept very soon. All right, now the next part is almost sure convergence. This is the strongest convergence that I'm considering today. So this means that there is also probability involved, but there is going to be basically the probability of the limit. So this means that the probability that the limit of a sequence is equal to, the limit of a sequence is equal to x, which x is supposed to be, is going to be equal to 1. Okay, so that means that almost surely, and the notation is AS. So events in which the random sequence does not converge to a limit has a probability 0. So in this case, basically, it is the probability of the limit rather than the limit of a probability. Okay, so when it comes to convergence in probability, that was the limit of the probability. And now, this time, this is the probability of the limit. And that's not the same. Okay, so the limit of a probability is not the probability of a limit, by the way. So you cannot bypass basically the probability and as well as the limit operators, respectively. Okay, so here again, the probability that the sequence does converge is equal to 1. So the probability that it does not is going to be 0. It is 0. Okay, so in contrast, so when you basically want to contrast that to convergence in probability, this means that the probability that the limit is not equal, so the limit of these members is not equal to x, this is going to be equal to 0 then. This is what it is, all right? And in the previous case, it was the limit of the probability, guys. Okay, so that's basically what it would be, okay? But keep in mind, that's not a straightforward issue in that regard, okay? So it's not just, bypassing, probabilities and limits, okay, when it comes to that. There is a relationship between these three types of convergences. Okay, I'm not sure if you can say the word. No. The first thing that I wanted to illustrate is that convergence in probability implies convergence in distribution. That's number one. Okay, so basically this is expressed like this. So convergence in probability is basically denoted by this error. Okay, when you have P at the top, and then this implies convergence in distribution. Whereas convergence, almost sure convergence, implies convergence in probability. So, and keep in mind, guys, you cannot basically turn that around. So, in general, you cannot go backwards. Okay, so convergence distribution does not imply convergence in probability, and convergence in probability does not imply almost sure convergence. Okay, so almost sure convergence, again, is only sufficient but not necessary for convergence in probability, and convergence in probability, on the other hand, is only sufficient but not necessary for convergence and distribution. Okay? You understand this, guys? Okay, so you cannot go backwards. There is more, okay? So there is just, I mean, you know, convergence and let's say in Rth mean or something like that, so convergence and mean, but I'm not going to consider that one. Usually this is not something that we need here. Okay, guys, now I will basically refer to these types of things here and there. The more important ones, especially in econometrics, are convergence in probability and convergence in distribution. Okay, almost sure convergence. Maybe you hear that term when I was saying the starting value is 0 almost surely. So, okay, I was saying, for example, that the starting value, let's say, of a process is 0 almost surely. This means actually, if you want to translate this, that the probability that the starting value takes basically the value 0 is equal to 1. Okay, so that happens basically when you have 100% certainty. But it doesn't really, it doesn't mean that it does. Okay, so some people say, okay, just because an event has the probability 1, it doesn't mean that will happen. It only means that from the theoretical perspective, we assign 1 to be that probability of this event. Think about the normal distribution, guys. So when, for example, just for the record, if X follows the normal distribution of some sort, it doesn't really matter what kind of parameters that you have. The probability that X takes a certain value is going to be equal to 0. Okay? So if you would say basically the process follows the normal distribution, the probability that basically the starting value would be equal to 0 would be literally 0 then. Okay? But we assume it's going to be equal to 1. Okay? If that was true, actually, from the practical perspective, you would not get a sample from the normal distribution. So just because an event has a probability which is equal to 0, it doesn't mean that it does not happen. And just because an event has a probability 1, it doesn't mean that it will happen. Okay, so that is contradicting the intuition, I understand. But it just means that we assign those events certain probabilities. Otherwise, basically the concept of probability would not work. And that's a problem. Okay? So the probability that if the random variable, let's say, follows a normal distribution means that the probability that it takes a certain value is going to be 0 for every value that is, this would mean that would be, from the practical perspective, if this would not happen, that you would say that from the practical perspective, there would be no samples that you could obtain from the normal distribution then. So no sample would fit to the normal distribution in that regard from a practical perspective, strictly speaking. You understand the issue. So there's a contradiction basically between, let's say, theory and practice in that regard. Okay, I could give you other examples illustrating that, but maybe you think about the geometric distribution. So there are also different types of things that are involved, okay, where you have basically limiting issues or regarding probabilities, and that's what, you know, you would need to consider. So yeah, we assign basically certain events. So for example, if X follows the geometric distribution, okay, and let's say the probability mass function of the geometric distribution is looking like this, so you might basically be familiar with it. Depend on how you count, so you have 1 minus p to the power of k times p. Then you could show basically that the probability that X is finite is going to be equal to 1. So that means, you know, the geometric distribution models the number of failed trials, you know, until a certain event happens. So this means that sooner or later, the event will happen almost surely. Okay, that is basically attached to it. It could be the case, let's say you play, let's say you gamble with your fellow students or whatever. It could be the case that nobody wins because nobody runs out of money. Okay? You play against a bank or something, and you know, it could happen that basically you win, you lose, you win, you lose, you win, you lose. You know, nobody's running out of money, and that goes infinitely. That goes basically, it doesn't stop. Okay, so that is some sort of perpetuity that is involved. But the event basically of that is assigned to be 0 in that regard. So sooner or later, this means that basically the experiment would stop almost surely. This is what you would need to understand here. Although from the theoretical perspective, it could be the case that nobody wins. Okay. Okay. Now, but again, I'm not going to discuss this here. This is not explicitly related to time series, but you should basically understand, so just because an event has a probability 1, it doesn't mean that it's going to happen. That's not equal. So if, let's say, probability that A is equal to 1, this does not imply that A is equal to omega. Okay? So basically that's not true. Okay? So that's not the same thing. All right, guys. Yeah, that's what I was basically what I'm mentioning here. Now, the central limit theorem, you might be heard of that. So CLT is the notation for it. It's a Lindenberg-Lévy version. There is different versions of the central limit theorem, of course. I will consider, so the Lindenberg-Lévy version considers basically random variables that are IID. This is basically the starting point of the central limit theorem in this case. Sometimes because, you know, that is a relatively strong requirement, by the way. So we need to also basically to relax this assumption here and there. But then the proof of the central limit theorem becomes much more complicated. I will talk about that in the context of time series also, because there is a central limit theorem involved regarding, for example, ARMA models. But that's not what the point is. Now, if it's IID, and it's denoted as mu and sigma squared, this means that the expectation of each is going to be equal to mu, and the variance of each is going to be equal to sigma squared, as we have already introduced. I mean, we were introducing this notation already, so that's what this notation means. So they all have the same expectation. They all have the same variance, but keep in mind they are not necessarily normal. So this notation reminds us basically the declaration of the normal distribution, but keep in mind that the random variables are not necessarily normal. If they have identical distributions, then they have also identical moments. You understand what I'm saying? Okay, so if they all follow the same binomial distribution, then they have the same expectations and the same variances, respectively, of course. Is it clear? All right, so that's what basically you would need to understand here. Now, if they're all IID, which means that they are independent and identical, okay, and in terms of identical, I mean identical distribution, then the following sequence that I'm going to consider. So again, so the sequence are, the members are here, this is x1, x2, and so on. Okay, so these are the members of the sequence, are basically generated from the arithmetic mean of the corresponding random variables. So you would take the arithmetic mean of the random variables, okay, and generate basically members here of the sequence from it. So that's why I was attaching, you know, an index to the arithmetic mean. If you don't understand what this would be, okay, then of course the first member is going to be 1 by n, or 1 by 1 basically, times the sum of from I is equal to 1 to 1, so this is going to be equal to 1. So that's x1, of course. The second member of the sequence, okay, that I'm going to consider is going to be 1 by 2 times the arithmetic mean of this 2. The third member of this sequence that I'm referring to is 1 by 3 times the sum of the 3. And that's that. So this is how you generate basically a new sequence. So keep in mind, I'm talking about the new sequence, not the sequence of these axes, okay, that are involved. So this is basically what it would be. You understand? So this is a sequence of arithmetic means. And a sequence of arithmetic means, okay, is, according to the central limit theorem, converging to the normal distribution. So you can say that simply is, okay? Now, in the case, I want to standardize that because I would need to look at the expectation as well as the variance of the arithmetic mean, okay? I don't use indices because you don't hate to, but I mean, you can, of course. So I want to be consistent in that regard. So the expectation is going to be equal to the expectation of each observation of the arithmetic mean, let's say. And the variance, but the variance is not, you might know this from statistics, the variance is going to be sigma squared divided by n, okay? So that's something that might change, okay? So if you, basically, you can confirm this result by simply just replacing the arithmetic mean by this expression. And then you would consider, I mean, if it's IID, there is no autocorrelation, let's say, or there is no correlation between them. So the variance of their sum is going to be the sum of their variances. But you need to understand how the linear transformations also work here. So the expectation of a linear transformation is the linear transformation of the expectation, but not the variance, of course. So the variance of a linear transformation is not. Pay attention to it, because then you would take out the multiplicative constant by squaring it, and the variance of a linear transformation does not depend on additive constants, but only multiplicative ones. You understand that, guys? So therefore, you have 1 by n coming out, okay, if you take that out basically from the variance operator in total, okay? But that's just a side note. Now, if you consider that, then this means that if you want to standardize this, you simply just subtract its mean and divide it by the standard deviation, and its standard deviation is going to be sigma by the square root of n, and this thing will converge in distribution to the standard normal distribution, and that's what the central limit theorem says. Okay, this notation means, okay, converging to a distribution, this means that it converges actually to a random variable, okay, that follows the standard normal distribution. But why would you basically declare that random variable? So you can simply just take that out and you can say, okay, that thing would converge to the standard normal distribution, of course, as the sample size is increasing. And that's what the central limit theorem is. Okay, so if you might not understand where these things are coming from, so again, then it's standardization. So what you see here is a standardization, guys. This test statistic, let me refer to it as such, is equal to x bar minus mu divided by sigma by the square root of n. So if you look carefully, that's the same expression. And that is a standardization of the mean. So this means, literally speaking, that the standardization of the mean of IID random variables would converge in distribution to the standard normal distribution. This is what the central limit theorem is claiming, according to that version. Okay, so there is multiple versions, basically, to the standard limit theorem. Okay, so sometimes you would need to drop the IID context because that's a very strong requirement, relatively speaking. Okay, it's very relatively rare that you have IID random variables, but anyway. Okay, so that's what basically what the central limit theorem is. I'm not going to consider the proof, okay, but that's how you would express it. Okay, is it clear, guys? Technically, I mean, if you want to refer to the convergence of the distribution functions explicitly, you would argue the following, so that the limit of the probability, I mean, what probability? The probability that the standardization, which I have here, so the square root of n times x bar minus mu by sigma, that the standardization is not exceeding k, that's it, right? So the limit of that, which I would basically express it as such, is going to be, and that's the usual notation, the cumulative distribution function of the standard normal distribution at that point. You understand what I'm saying? So what you see here on the right-hand side is going to be the cumulative distribution function of the standard normal distribution, okay, so in green. And what you see here, okay, in this part, is the cumulative distribution function of the standardization of the arithmetic mean, and the standardization of the arithmetic mean is actually, you know, the square root of n times x bar minus mu by sigma, okay? So that's basically what you see as the limit. So when it comes to, you would need to explicitly refer to the cumulative distribution functions in this context, okay? So that's what the central limit theorem is. Now, guys, again, yeah, you got a question?
Yeah, so I have seen already the standardization in my statistics lecture, and
sure.
There was now this n under square root, and I'm wondering why is it there?
Because it's a variance. It's coming from the variance of the arithmetic mean. There was, trust me, there must have been, because if you don't have that, then it's not consistent with the central limit theorem. So again, you would need to consider the expectation of the arithmetic mean, or a sample mean, let's say, and the variance of the sample mean. And the variance of the sample mean is not sigma squared, okay? So it's not equal to basically to that. It's equal to, you know, to sigma squared by n, okay? Now, whenever you have the normal distribution around, you need to understand that if x follows the normal distribution, some sort of random variable with mean mu, and, or let's say mean a, and variance b squared, then the standardization of x will be just that. You understand what I'm saying? This will follow the standard normal distribution, okay? So if this follows basically the normal distribution with mean mu instead of a, you would need to drop it here, okay? And if b squared is equal to sigma squared by the square root of n, sigma squared by n, not the square root of n, then b is going to be sigma by the square root of n. This is where the square root is coming from. You understand? So this is due to the fact that, you know, you have the standardization involved. Okay, is it clear? I'm recording this, guys, so you don't need to take pictures. You can watch the video if you like. You can, of course. You can make your screenshots from the video if you like, if that is important. So that has something to do with the standardization. You understand? So that's basically it. All right? And yeah, so this is where it's coming from, because this expression, on the other hand, okay, it has a double fraction in the denominator. This is equal to that statistic that you see. So this is equal to the square root of n times x bar minus mu divided by sigma. And I like to use that one, okay, because this is, I mean, this, you know, the square root of n is called also the convergence rate, okay, because you have mu, which is the expectation of the random variables that are involved in the sample mean, and sigma is the standard deviation of the random variables that are involved in the sample mean. You understand that, guys? But you don't have that basically when it comes to the standardization. Okay, so this is where it's coming from. And you must see it. Otherwise, it's not correct, you know. So just for the record, you know, x bar minus mu divided by sigma does not converge in distribution to the normal distribution of any sort. Okay, that will not be normal. Okay, because it's, you know, it's not the standardized version. You need to standardize it. And by standardizing, I mean, you would need to basically refer to the standard deviation. All right, is it clear? So yeah, good. Now, I just basically want you to mention that. Okay, and I would also consider the weak law of large numbers. That means there is some sort of convergence, another type of convergence. This means that the sample mean, guys, converges in probability to the mean of the random variables. So that's the weak law of large numbers there. Okay, if the random variables are IID. Okay, you understand that? So if the random variables are, I'm going to prove that statement, by the way. So this is easy to prove. I'm going to show you. Okay, but the first thing that you need to understand, for example, is that the sample mean of the noise. Okay, so the sample mean of a noise. Now, what is a noise, right? So you know what a noise is. I mean, IID noise in that regard. So let's say you have an IID noises with mean 0 and variance sigma squared. Now, since the mean is 0 and the sample mean would converge to the mean, that this means that the sample mean of the noise would converge in probability to 0 as the sequence, or as basically the sample size would be increased. So I was denoting the sample size by capital T, so I want to be consistent regarding that notation, but the sample mean of the noise would converge in probability to 0 based on the weak law of large numbers. So if the weak law of large numbers is true, then it's also true for noises, obviously. Okay, so especially IID noises. They don't even have to be IID in that regard. But if they are, it's enough basically for them to be uncorrelated, by the way, but that's a different version. Okay, that is even a weaker concept. Now, there is a weak law of large numbers and there is a strong law of large numbers, but most of the time I see weak law of large numbers in econometrics, so I would not refer to the strong law of large numbers, but when it comes to the strong version, so again, the weak version is coming from convergence in probability, and there is also the strong version, and the strong version just simply replace the convergence of the sample mean by almost sure convergence. So that is going to be the AS convergence. Okay, so that's the strong version, and then you have the weak version, because convergence in probability is a weaker concept than convergence, or almost sure convergence, sorry. That's the expression. All right, but again, in econometrics, we have the weaker version most of the time. So I will stick to that. All right, now, again, so you need to understand that the noise, or the sample mean of the noise, satisfies that, and the probability limit of the sample mean is going to be 0. So that means that, again, so the sample mean of these IID noises will converge in probability to 0 as the sample size increases. Okay? Based on the weak law of large numbers. So this is an implication of the weak law of large numbers. Now I want to prove that. Okay, so it's not difficult. Technically, it's actually relatively simple if you're familiar with the Chebyshev inequality. The Chebyshev inequality is making a statement about the distance, or let's say the probability, of a random variable taking a distance which is basically above its mean. So let me say, I would need to consider that one for, let's say, another random variable which I refer to as y, and let's say it has mean a and the variance b squared. Okay, it's not necessarily normal. Now, this means, according to the Chebyshev inequality, that the probability that the random variable has a greater distance to its mean than, let's say, a pre-specified value. Okay, so it's greater than equal to, but if it's equal to, nobody cares. So actually, whatever. So for example, if it's normal, then it would be 0, but it doesn't matter. So this probability, okay, is bounded from above. And the limit, or let's say the upper limit, you can say, is basically sigma squared divided by the square of the distance. And sigma squared is the variance. So again, you have some sort of relationship here for specific values, of course. And yeah, of course, that is also trivial. So for example, this is interesting if, let's say, epsilon is, relative, for a larger version, because, if epsilon is relatively small, then you would have a number coming out which is greater than 1, but every probability, or any probability, is not greater than 1, so that would be not an issue. So this is an interesting statement, guys, if, let's say, epsilon is relatively large in this case. Okay, but it doesn't really matter. Now, so this is the Chebyshev inequality for an arbitrary random variable, making a statement about the probability of a random variable having a distance which is greater than the mean. Having the distance to its mean which is greater than the pre-specified value. And that probability is bounded from above by this expression. Okay, so it cannot be greater than that, no matter what. Okay, now I will take this, apply it for the sample mean. So the sample mean, as I mentioned before, has an expectation which is equal to the sample observations, but the variance of the sample mean is not equal to the sample observations. This is going to be equal to the variance of the sample observations by the sample size, okay? So that's why you had the expression, the square root of z, at the test statistic when it was the central limit theorem. But anyways, so if you apply the Chebyshev inequality for the sample mean, you'll find that the probability that the distance between the sample mean to the observation and the sample mean, guys, and the mean of the observations having a value which is greater than some sort of pre-specified distance is not greater than the variance divided by the square of the distance. Now the square of the distance is of course epsilon squared. That's true without a doubt, but the variance is of course sigma squared divided by n. And if you have sigma squared divided by n divided by epsilon squared, this yields sigma squared divided by n times epsilon squared. Okay, so that's basically what comes down to the Chebyshev inequality for the sample mean of the random variables. Okay, now what you can do, I would take that, write it down, as you see, I'm just simply copying it. So this is just a copy. And then I take the limit on both sides. So the limit of the left-hand side is of course equal to the limit of the right-hand side of the inequality, even if if this is an equality. Okay? It's not equal to, so because it's not an equality, but it's an inequality, but that doesn't matter. So if, let's say, A is not greater than B, then this implies also that the limit of A is also not greater than the limit of B, okay? Even when it comes to sequences, okay? So when it comes to sequences, that's not going to be an issue, all right? So if members of a sequence A are neither greater than members of the sequence B, then the limits, if their sequence converge, they're not basically that either. Now, what happens to that? Okay, what is the limit of this expression? Of course, sigma squared is a constant, epsilon squared is a constant, n is increasing. So if n is increasing, this means that the denominator increases. So therefore, the total expression would converge to 0 then. So this means that the probability, since this is not going to be greater than that, this means that the probability, the limit of the probability that we're talking about is equal to 0. And that is basically convergence in probability by definition. So this implies basically that the sample mean converges in probability to its theoretical counterpart as basically the sample size increases, and this is the proof of the weak law of large numbers, guys. So it's stunningly easy if you have the Chebyshev inequality around. Now, of course, you would need to prove the Chebyshev inequality first, right? But that was a major step, actually. So I don't know if you heard about that inequality, but that was a major step. And the proof of the Chebyshev inequality is not that straightforward, by the way. But let's say we already have that handy, so I mean, that is its form. A major application, by the way. Anyway, so this means that, again, the sample mean, sorry, I was forgetting it here, the sample mean of these random variables would converge to the expression mu. Okay, so that is, I need to fix this slide, guys, unfortunately. So I was just copying it without thinking about it. So the sample mean would converge in probability to the theoretical counterpart in probability, of course. Is it clear, guys? Okay, so that's basically the proof of the Chebyshev inequality. Now, an estimator is called consistent, and that's going to be another issue if it converges in probability to its theoretical counterpart. Okay, keep in mind, guys, that the estimator is a random variable, and this is a constant most of the time, so parameters are constants. Okay, one of the examples is going to be, I mean, since the sample mean converges in probability to its theoretical counterpart, this means that the arithmetic mean is consistent. Okay, is a consistent estimator for the parameter mu. Okay, you might hear this in statistics because of the weak law of large numbers, right? So the weak law of large numbers literally says that the arithmetic mean of a sample, if sample observations are IID, I forgot to say this, if sample observations are IID, then the arithmetic mean of a sample is a consistent estimator to its theoretical, for its theoretical counterpart. You understand that, guys? Yeah, so actually, this is an example, and that's, you know, what consistency actually means. Now, in bachelor's, I mean, undergraduate courses, this concept is not considered. So actually, this implies, consistency implies, okay, among others, that the limit of the expectation is basically 0, and that the variance, the limit of the variance, sorry, not 0, it's actually, I mean, sorry, I was using a wrong notation, so this is going to be equal to that, so at least, you know, you have asymptotical unbiasedness, and the limit of the variance is going to be 0, but keep in mind, guys, that this is just an implication, okay? So just because that it is true, actually the estimation is not necessarily consistent, okay? So that is not a one-to-one relationship, okay? So consistency is only sufficient but not necessary for that. But that's what you were taught in undergraduate courses due to simplification, right? Okay, so I was lying to you when I was saying that consistency means that the variance of the estimation is converging to 0, but that's just an implication of that. You understand what I'm saying? I apologize. Okay, it's okay. Right? Anyways, okay, now again, the weak law of large numbers says that the sample mean of IID variables is consistent for its theoretical counterpart. That's what it is. Okay? Actually, it's not just consistent, it's also unbiased, but that's not what the weak law of large numbers says. It's unbiased and it's also efficient if sample observations are normal, for example. There are also other sufficient conditions for efficiency, but again, I'm not considering this, okay? I'm not teaching you statistics predominantly. Anyways, now there is a central limit theory version for ARMA models. Now, why is that basically a new version? Because keep in mind, guys, that if, let's say, a process follows an ARMA model, you know, autoregressive moving average one, it could be just simply also an autoregressive one So that includes also any autoregressive model, and that also includes any moving average model, okay? And this means that, of course, that Y is not IID, right? So that's the issue, okay? Not in general. I mean, you can set every parameter being equal to 0, and then it could be the case, but you understand the issue. So therefore, the Lindenberg-Lévy version of the central limit theorem is not applicable of the sample mean of an ARMA or a stationary ARMA process, okay? Now, so let's say Y is a stationary ARMA process. It needs to be stationary in this case. If it's not, then central training would not be applicable, not even directly, not even indirectly in this version. But again, this is a new version. And keep in mind, guys, there is autocorrelation between current and past observations of the process in general. We were calculating the autocorrelation function of an ARMA 1-1 model. You might remember that. Okay, so it's not IID then, okay, if it's basically autocorrelated. Cannot be, but again, it doesn't really matter. So you can apply the central limit theorem, but need to be a little bit more creative. I will introduce you to that version, okay? So again, YT bar is a sample mean of the ARMA process. By the way, this is also true for other processes, not just ARMA models, but ARMA models are relatively common, so I will stick to that one. Okay, so that is basically the largest class of models that we had. Okay, so again, YT bar is a sample mean of the stationary ARMA model, you know, when you observe a sample. So the sample is basically, you know, Y1, and you have observations from Y1 to YT, you know, denoting basically specific points of time. And then you have the expectation. Now, whatever the expectation is of the ARMA model. So when it was basically an AR1 model, the expectation was, if I recall it correctly, V by 1 minus A, right? Okay. So, and yeah. And when it was a moving average model, okay, that was just simply, the expectation was just simply V, was the constant, by the way, right? So again, whatever that is, it doesn't really matter. So the expectation, and then multiplied by the square root of the sample size. Now I was not using the standard deviation here because I was putting that into the normal distribution to which it converges. And you will find that the standard deviation has the mean 0, so that is, of course, you know, at least, you know, the mean is standardized regarding that. If you subtract basically the mean of a random variable, that the mean of the new random variable would always be 0, and so is the limiting. So is the mean of the limiting distribution, by the way. But that's not going to be standard normal. The variance is going to be omega squared. And omega squared, you might remember this, is the long run variance. So here comes back the long run variance here in this expression. So one of the things that I mentioned before, I mean, that was yesterday when I was introduced to the long run variance. So this is the long run variance. So long run covariance, some people say long run covariance. It doesn't really matter. In a multi-dimensional case, it's a long-run covariance matrix. But you can refer to it as a long-run variance if you like to. I don't mind. So anyways, so let's call it long-run covariance then. Okay, so that's going to be the variance of the limiting, basically, of the limiting distribution. Now, the problem is you cannot simply just standardize it, okay, because there is an issue involved in here, okay? So first off, how would you address those? This is just a limit, guys. So there is also a limit involved, and what I will show in my PhD classes, I'm not going to do this here. So again, as the sample size increases, this is the version, but you cannot simply just take that out, basically from the normal distribution by using standardization, okay? I mean, you could literally say that square root of t times y bar, sorry, so in this case it's called y bar, minus the expectation of the process, divided by the square root of the long run variance, maybe you can call it the long run standard deviation or so, that would be converging to the standard normal distribution. That would not be basically wrong, but there is an issue involved in here, okay, regarding the standard deviation here, okay, so that's not technically not that wrong, but it's basically not feasible, and the reason why is that not feasible because the long run variance is the limit of the variance of this test statistic. I cannot do this right there, but I mean, you could basically try to break it down if you like to. And, but you need to express basically how to do this. So this is the limit of that. Okay, and that's why it's not feasible directly taking that out from the normal distribution that is involved, even from the theoretical perspective. So you have a limit of a limit, let's say, in that regard. Okay, now why? And that's the question, why? And the reason is, of course, because, again, ARMA is not IID. That's the reason. So keep in mind, this is a different version of the central limit theorem, a new version, if you like. Okay? And, yeah, there is basically, but I can give you the intuition for that. Okay? So when it comes to the central limit theorems, guys, so because that's a difference here. Okay, so let's say when it comes to the central limit, and I would try to put that in terms of the previous notation. Okay, the statement was the square root of n, and I would do that, times x bar minus mu would converge in distribution to the normal distribution with mean 0 and variance sigma squared. And the reason, of course, being is the variance of this test statistic that you see here. So the variance of the square root of n times x bar minus mu, the variance of the test statistic is equal to sigma squared. So this is where you find it again. Okay? So this is where you are regarding it. Okay? So again, I'm talking about this test statistic. Let me emphasize that a little bit more better. Okay? So the square root of n times x bar minus mu. Okay? In this regard, you could check that for yourself, that the variance of the yellow test statistic would be equal to the variance of the limiting distribution. And then you could take it out. But when it comes to the central limit inversion or ARMA model, this is not the case. This is the limit of that. You understand? That's the difference. And the reason being is, of course, you have autocovariances involved. In this case, the random variables, x1, x2, and so on, were all IID, all right, which they're not in case of an ARMA model. You understand what I'm saying? So then you would take the limit of those, because there is covariances involved in this regard. You understand what I'm saying? So that, I mean, just from intuition, okay? First off, I would need to prove the central limit theorem, and then I would need to prove it for, basically for the ARMA models. But the long run variance is basically playing the key role here, okay? Because this is, in this case, this is the limit of that. All right? You understand it from the intuition? Okay? And that this is one of the major reasons why I was actually introduced you to the long run variance, to establish basically asymptotics that are involved with certain stationary processes. Now, for non-stationary processes, this is not going to be true. Okay, so it needs to be stationary. If it's not, then the sample mean of that will not converge in distribution to the normal distribution. Okay? But at least this means that you can establish some sort of estimation regarding the sample mean of stationary ARMA models, by the way. But again, that's what it is. All right, now I'm going to also consider so-called ergodic processes. Ergodicity is a term. Okay, that is a process which is stationary. So that's number one. It has to be stationary. So if it's not stationary, it cannot be ergodic. Number one. And number two, its sample mean converges in probability to its theoretical counterpart. Okay, so again, mu is the theoretical counterpart. Okay, so keep in mind, since the process is stationary, the expectation is time independent, of course. Okay, so that's not going to be an issue then. Time independency, what you have here. Is it clear? All right, so this means, and this has to be basically both. Now, there is processes which are stationary but not ergodic, and I want to address one of them. Okay, so I'm going to consider one of them. And the one process that I'm going to define is looking like this. It is a noise plus a random variable. And the noise is IIT, and the random variable is normal. Okay, so you have a normal random variable with, let's say, mean mu and variance 1. And I'm going to show you that this process is stationary. I mean, it is stationary, clearly, because, of course, I mean, when you look at the expectation, right? So the expectation of that is going to be the expectation of a sum, and the expectation of a sum is the sum of the expectations, blah, 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 right? So, and then that is also true for the variance because they don't depend on each other. And that is also true for the autocovariance because noises are not autocorrelated and there is no autocorrelation involved regarding the random variable. That is normal, right? So again, y is stationary. And that's relatively easy to see. Now, if you want to basically to check what the mean is, because I would need to look at the probability limit of it. So I want to compare the probability limit to its theoretical counterpart, because if it is equal to its theoretical counterpart, then the process is going to be ergodic as well. But it's not, I mean, it's not going to be the case, as you will see. So I would check what the theoretical mean is. Again, the expectation of a sum is the sum of the expectations. You might know this. And the expectation of a noise is 0. The expectation of the normal variable is mu. So you have mu plus 0, which is equal to mu then. Okay, and that will not be the probability limit of the sample mean of this random variable, or let's say of this process. I'm going to basically address it, so you'll see. I'm going to calculate the sample mean. Or let's say I'm not going to calculate it because I don't need to. I don't have sample observations, so not directly, but I'm going to look at basically the random variables that are involved. So this is going to be 1 by t times the sum of these random variables, okay? And the sum of these random variables consists of basically sums themselves. And then what you can do is you can split the sum, right? So you can split it. So you have 1 by t times the sum of these m's, which is equal to m, by the way. And then you have the sample mean of the noise, okay? And then that's it. So the sample mean of the noise plus these m's, or plus m, let's say, and that's going to be m plus the sample mean of the noise. Now, you might know this, okay, that the sample mean of the noise satisfies the weak law of large numbers. So according to the weak law of large numbers, this has a probability limit which is 0. You understand what I'm saying? Now, limits are additive, so that means that the limit of a sum is the sum of the limits, okay? So therefore, I mean, you could have, all right, so that's basically what you have down there. You would need to consider m as well, okay? So we would add it to it because the limit of m is m, okay? It's not a sequence, by the way, so, well, let's say it would be always the same. And yeah, so this is not equal to its theoretical counterpart. So the probability limit of the sample mean of the process is not equal to its theoretical counterpart. So that means that the process, although it's being stationary, is not ergodic. Okay? You understand that, guys? So just because the process is stationary, it's not necessarily ergodic. But if it is, and why is ergodicity an important concept? Now, this is basically what the weak law of large number would yield. Okay? So this is the probability limit of basically of this sequence, all right, of the sample mean, by the way. But that's not equal. Okay, so I would continue here. That's not equal to its theoretical counterpart. Now, since it's not equal to its theoretical counterpart, then the process is not ergodic. Okay, so that's simply just that. Okay, now next time I'm going to give you some ideas how to test things when it involves basically autocorrelation. And for that you would need to use sample observations of stochastic processes, which I didn't define yet. Okay, so of course within the context of, let's say, linear regression, where you have an effective sample of the response, an effective sample of the predictor, but that's not what I'm going to use to. So let's say you have a sample of a stochastic process, and then you would calculate the sample mean. Now the sample mean, you don't need to, again, guys, you don't need to put an index here if there is no convergence involved, okay? So as long as there is no convergence involved, that's not a necessity. You can, of course, but that's what the sample mean would be. That's simple. Now the sample variance, so you can call it empirical variance. This is not a, the corresponding estimation. This is the notation, by the way. So we write sample variances of processes using gamma and 0 means that the time lag is 0. You can generalize that because the sample variance and sample covariance are literally the same thing. If for the sample covariance, or autocovariance to be precise, the time lag is equal to 0. You understand what I'm saying? So this basically is put together. That's why it's expressed by gamma. Now, since it's an estimator, we use gamma hat. All right? So this is 1 by n times the sum of the squared deviations from the observations of the process minus its sample mean. That's not surprising. Okay, but when it comes to the sample autocovariance, it's going to be difficult. I mean, I was telling you that for the covariance or sample covariance, this was basically for the first part of our lecture. Okay, when I was introduced to, when I was reviewing, for example, the linear regression, this is the sample autocovariance is not consistent with the sample covariance of basically regular data. When it comes to time series, you have 1 by t, but is done differently. So the sum starts at point 1, but it stops at point t minus h because the time lag is h. Okay, why does it stop at t minus h? Because there is no summons anymore. So keep in mind, guys, if you would consider that, you need to have observation pairs of some sort. And you cannot have basically more than t minus h pairs if the time lag is actually h. All right, so the first pair, or the first basically part, is the mean, or the difference between the sample observation to the mean at point t. And then you have the sample observations at point t plus h times or minus the mean here. Okay, and you could not break it down, unfortunately. So this is not equal to the mean of the products minus the product of the means. That should be obvious. Okay, because when it comes to, let's say, the observation at time point t plus h, you could not go beyond the sample size t, whatever that is. So the last part for t can be only t minus h then. You could not go beyond that because you don't have more than capital T observations. Is it understandable, guys? So, but again, that's what the sample autocovariance would be. And the sample correlation, so again, I will elaborate on that next time because I want to do hypothesis testing, especially for detecting autocorrelation. Sample autocorrelation is simply just, sample autocovariance by the variance. That would be the product of the standard deviations, but usually when it comes to stationary processes, the product of the standard deviations would be equal to the variance because the standard deviations are time independent. Okay? Usually it only makes sense to do this for for stochastic processes. There are stationary, but that's done anyway. Okay, so we would examine basically more or less the asymptotic behavior of these moments. I could call them moments. I'm not saying that they are, but I call them moments to basically be a little bit more general. Okay, it's not the moments, but let's say call them this way. When it comes to basically stationary stochastic processes. Now, I want to mention something. Why is ergodicity is an important concept? Because ergodicity ensures that at least the sample mean and the sample variance, and as well as the sample autocovariance, would converge in probability. So they can be estimated consistently for a stationary stochastic process, but any ergodic process is stationary. So ergodicity allows us just to do that. Okay, so let me just summarize that statement that is involved. Okay, so when it comes to basically ergodic processes, then of course the sample mean converges in probability to its theoretical counterpart. That's not surprising because that's true by definition, and it is also stationary, so that's not surprising. But this allows us to estimate, basically the mean of the process consistently from the sample empirical counterpart. You understand what I'm saying? So if the process is ergodic, ergodicity is sufficient for that. Okay? Stationarity is not. Ergodicity is. Not when is what is I mean, when is a process ergodic, that's another topic. But you should understand that this is, on the other hand, sufficient for the possibility that the theoretical mean of the process can be estimated consistently by using its sample analog. Okay? So that is, you know, a concept which ensures that. And that is also true, I mean, this is the same, and that is also true for the second moment as well. Okay, so that is literally the second moment. So since both the first and the second moments can be estimated consistently, and that is also true that is also true by the autocovariance, by the way. The mean and the variance of ergodic processes can be estimated consistently by basically using the sample analog. That's it. That has to do with some sort of summability properties, which are, again, also going to be sufficient, let's say, for ergodic processes, but I'm not going to talk about those. Okay, so ergodicity allows us to do that. And that is also true for the autocovariances as well. That's just a shift, by the way. Autocovariances of stationary processes tend to be decreasing as the time lag increases, by the way. Even though the correlograms would indicate it otherwise. Sooner or later, that is a tendency which is actually true. All right? All right, guys. So, yeah, since I was stealing your time last week, I would finish earlier today. Are there any questions, guys? No questions? Okay, so you have a new assignment. I tried to finish the last ones this weekend, but unfortunately I couldn't. So that much too. I was underestimating that, to be honest, unfortunately. But again, anyway, you're going to get your results anyway. So sooner or later, it is not going to be an issue. I mean, I have to, so it's not going to be a problem. But I try to complete your results until the end of this week. I'm not sure I would make it, but at least the 3rd and the 4th and the 5th, at least those. Okay? Okay, guys. Yeah, that was it for today, and take care. Thanks.